So let me share my screen. So I think in the last class we were talking about the propagation or propagation of electrons or ions through a medium which contains an electric field, a fluctuating electric field, and from there we had actually gone ahead and calculated. Sorry, just a minute. Just a minute. Yeah. So, and from there we had gone ahead and derived the condition under which a radio wave will be reflected from a particular ionized layer. And we had also made calculations for that. We had also done some small calculations, because since we knew the peak electron density for the DE, F1 and F2 layers, so we could see that basically, of course, these are values over the Indian region. Okay. And I don't have the scope of going too much into the details of the variabilities of ionization, but one of the important variations in ionization is from one place to another on the surface of the earth. That means the kind of ionization that you get, ionization density that you get over Kolkata, if you go simply to Trivandrum or Bangalore, then that is going to change. Okay. And if you go to maybe some place in the US or Europe, then that is going to be much less than these values of 10 to the power 5 or 10 to the power 6 per cc. Once again, if you go to the polar regions, either near the North Pole or the South Pole, then these ionizations are going to be high. Not of this value, but definitely somewhere around this value. So on the basis of that, we had calculated and found that the corresponding critical frequency, which is the highest value of the plasma frequency or the highest frequency which will be reflected back at vertical incidence. That means you start transmitting a signal and you go on increasing and you start getting the reflections from some layer, and as you go on increasing the frequency from the ground-based transmitter, gradually you probe deeper and deeper into that ionized layer, and beyond a certain value of frequency, suddenly you find that there is no reflection. So that happens when you have penetrated that particular layer. So that essentially means that for each different layer in the ionized atmosphere, you have a critical frequency, which is the highest frequency which will be reflected back at vertical incidence. Okay, so you can understand that this critical frequency is a very useful parameter. But as far as long distance propagation is concerned, this background condition of vertical incidence does not serve any purpose whatsoever, because if you transmit a signal at vertical incidence, it will simply come back after reflection to that same place. So there won't be any baseline. There won't be any distance covered between the transmitter and the receiver. So that's why later on we will see that we actually have to translate or convert these vertical incidence frequencies to the corresponding oblique incidence cases. So for the D to the F2 layers, we have found that the values of these critical frequencies, they range roughly from about 0.9 megahertz or 900 kilohertz to about 20 megahertz. Okay, so that's a fair range of values that we have over regions like, say, Kolkata and its surroundings. Now, let us move ahead and consider the second condition. That means where we have this propagation of electrons or ions in the presence of a magnetic field. So as I was mentioning in the last class that we had assumed the electric field to be fluctuating because of the fact that the ionization density that varies with time. So because early in the morning you have very little ionization over a particular place, and with the progress of the day, gradually that ionization density picks up and reaches higher values. It has its diurnal maximum. That means over a whole day, the maximum value is reached in the local afternoon hours, like from 12 noon to about 3 in the afternoon, or 15 hours. Then it starts to fall. So that's why, because there is a variability in that ionization density, the corresponding electric field which results from that charge separation, that is also assumed to have some kind of a variation. Now that variation is not a very simple sinusoidal variation, but because we could eventually break down all kinds of complicated waveforms into some form of sinusoidal or cosinusoidal waveforms. So that is why we have assumed the electric field in the previous case to have a simple sinusoidal or cosinusoidal variation. But when it comes to the question of propagation through magnetic field, now this magnetic field is the geomagnetic field that we are talking about, and we have mentioned in the last class that it is assumed to be more or less constant over a period of millions of years. And usually the geomagnetic field it changes, but that change is not significant enough to disturb the long distance propagation of radio waves. So basically the situation that we have is that when there are ions in motion in a magnetic field, then they experience a force. So you can see the condition that the ions are moving with a velocity which is at right angles to the magnetic intensity of that particular field. So the force which is experienced, that is given by the product of H into E. E is the electron charge into V. Okay. What is important is that this force is at right angles to both this velocity as well as the magnetic intensity. So if we try to form the equation of motion for that particular kind of particle, we could say that the centrifugal force due to this circular motion, that should be equal to the centripetal force due to the magnetic intensity. That means this mv square by r, that should be equal to this he into v. So from there we get this relation v upon r is he by m, where this v upon r is nothing but the angular velocity omega. Okay, so we could say that that is given by the product of he into m. So that means one important understanding that we can have from this relation is that depending on the particular species, that means this m is different for different species, okay, of particles. So depending on that, the value of this omega will be different, because h and e are more or less constant. E is constant definitely, and this h, that is also supposed to be constant over the periods of time that we are interested upon. So from there we could write that this frequency, some kind of a frequency, if we imagine, which is given by omega upon 2 pi, so that will be he by 2 pi m, and that frequency is known as the gyro frequency. Okay, and this gyro frequency, we could say, is the frequency of circular motion of a free ion in the geomagnetic field. So the situation is something like this, that is, if you have, these are the magnetic lines of field or force, then these particles, they cannot escape out of this, and so they will be progressing in the direction of the field and form this kind of a helical or spiral around these lines of force. So this is the kind of motion which will be there in case of the elementary particles, whether electrons or ions. And now in the upper atmosphere, if you just put the values of these, the values of h, e, and m, then you get, this will be like, this gyro frequency will be something like 1.5 megahertz for the electrons, and about 50 hertz if you consider atomic oxygen. That means if you put the corresponding value of m for atomic oxygen, then you will get the corresponding value of this gyro frequency, something as 50 hertz. So this variability of, or this motion propagation in the presence of a magnetic field, this leads us to the gyro frequency, while when we had considered the case of motion of ions or electrons in the presence of a fluctuating electric field, that has given us the expressions for the plasma frequency as well as the critical frequency. Okay, the critical frequency is just a special condition of the plasma frequency that we had seen earlier. So having proceeded this far, we should also try to understand that we have been talking about, this radio sounding. Okay, the radio sounding of the ionosphere, that means the vertical incidence propagation. So far, all the theoretical background information that we have gathered we should try to put it into some kind of an instrument. That means there has to be some kind of a practical instrumentation which will be able to transmit radio signals vertically and give us the corresponding information about the critical frequency over a particular location. But then again, we have to remember, if we just consider one of these cases that we were talking about, I think in the last class or somewhere, yes, that is, if you consider that you have a transmitter here and a receiver there, and the baselines are of the range of say 1000 to 2000 or even more, then simply having the value of the critical frequency over the transmitter or over the receiver location, that will not help, because this signal will be traversing across different geographical locations. So you will need to know that what are the critical frequencies at all these intermediate points, at least at some of the intermediate points. The rest we could interpolate, but it is always better if you have as many number of actual or real-time measurements as possible. So once you have the critical frequencies or the vertical incidence propagation frequencies available from these intermediate locations, then we would be able to make the corresponding conversions to the cases of oblique incidence propagation, because until and unless you could transmit the signal in an oblique incidence direction, in an oblique direction, you won't be able to cover any effective baseline. So that means there has to be some kind of a conversion, but before that we need to have some understanding of how we could actually calculate the value and the information about the critical frequency using some kind of an instrument. So one of the first kind of radio sounding, this particular term is similar. I mean, sounding of any particular medium or any particular object essentially means you transmit some kind of a signal, whatever that may be, and you get its reflection back. And from the reflected echo, you try to understand that what is the distance of that object from which you have received that reflected signal, and what are the properties also. It may be possible that to understand that what are the properties of that medium from which I have received back the reflection. So there is a pulse method, that means simply sending out small pulses of radio frequency energy, and which was first introduced by two scientists, Brait and Tube. That was way back in the 1920s. And our own founder of the radio physics department, Professor Shishir Kumar Mitra, was one of the pioneers in this field. Okay, he was instrumental in assembling the first, manual, this kind of a sounding system in Asia, and he did that around the 1930s. So essentially in this pulse method, we have a short pulse of radio frequency energy of typically say about 50 microsecond duration, which is transmitted vertically. And then the velocity with which the pulse travels, of course, that is what is known as the group velocity. And that group velocity we have seen while discussing about the propagation of electrons or ions through a medium which contains a fluctuating electric field, that the group velocity is related to the free space velocity of light through the radio refractive index. And that radio refractive index we have seen, that is in a way related to the electron density which is present in the medium. And from there we have found that up to the height of maximum ionization, the electron density changes or increases with height, and so the radio refractive index that decreases with height, that means essentially there is a movement or propagation of these transmitted signals from a more denser medium to a rarer medium. So there is some kind of a deviation of those radio signals away from the normal. But if we consider the case that we are only interested in the vertical sounding of these ionized layers, then if we consider the situation that the group velocity is related to the free space velocity through the radio refractive index. Now, since the group velocity is less than this, because of course the radio refractive index, we know, we have seen that expression that the radio refractive index is given by this kind of a relation, that is this mu is square root of 1 minus 4 pi into Ne is squared by m omega square. So because this is a finite term, so that means it's a non-zero term. So that means the value of mu will always be less than 1. So keeping that in mind, we can conclude that the group velocity will always be less than the free space velocity of light. So that means that particular radio signal which is transmitted in the form of short pulses of radio frequency energy. So that particular radio wave will propagate with a velocity which is less than the free space velocity of light. So in traversing a particular distance, that particular signal or wave will take a longer time, right? The velocity is less, so in propagating a particular distance, it will take a longer time. So there will be some kind of retardation, okay? Some kind of a retardation which is known as group retardation, which will take place. So if you simply follow the principle that that people use to calculate the depth of an ocean, if you remember, there were very interesting problems like from a ship you send an acoustic signal vertically down so as to get its reflected signal or reflected echo back from the ocean bed. And because that was an acoustic signal, you used to multiply the velocity of sound by half the time of propagation that elapses between the time you transmitted that acoustic signal and the time you received that. So you simply halved that time interval, half of that time interval multiplied by the velocity of sound in that medium. That would give you very easily the depth of the ocean. But here, if you follow an exactly similar principle, then what will happen is that if you calculate that this is the signal propagation time by simply noting the time difference between the transmission of the signal and getting back the reflected echo, then that time will be, of course, higher because the wave is not propagating with the free space velocity of light but with the group velocity, which is less. So if you multiply that or use that signal propagation time, then you will get a corresponding height which is kind of virtual, not the actual or not the real height of reflection of the signal, which will be always greater than the actual height reached. That means because it is not that someone is moving up along with that radio signal and making the measurement or noting the exact point from which the signal suffers reflection in the ionized atmosphere. Nobody is doing that. There are no instruments which is moving along with that radio signal. So what we have is a ground-based technique. That means we simply use our information, our background information about the ionized atmosphere in order to calculate the height of reflection. Okay, so that height of reflection will be some kind of a virtual, not the real or actual one, and it will always be greater because of the group retardation phenomena. The group retardation takes place, so the group velocity becomes less than the free space velocity of light, and so the signal will take a longer time in propagating. Okay, so when it does happen that way, then essentially the height of reflection calculated that way will be greater. So if we consider, if we try to find out a relation, between the real height of reflection and the virtual height, then we could say that if we consider an incremental time dt, and if we want to find out that what will be the height that a wave group will travel in that incremental time dt, so that will be simply given by this Vg, the group velocity, times dt. Now, in a dispersive medium like the ionized atmosphere, this group velocity is related to c through this radio refractive index. So, if you just put the value of your group velocity in this expression, you get that dh will be mu c into dt, and in place of this c into dt, you can write dh prime. Okay, this is the increment in the virtual height. That means the wave is not traveling with c, but it is traveling with Vg. So this c into that incremental time will be some kind of a virtual, it will be some kind of a virtual increment in height. So your dh prime, that will be given by dh by mu, and from there, if you would like to if you would like to do the integration, it will be like integration dh upon mu. So this is some kind of a relation which connects the actual height of reflection with the virtual height of reflection. So, as I was mentioning, that the founder of our department, those of you who have the opportunity to come to our department during the last 1 year or so, you must have noticed the statue right next to our entrance of Professor Shishir Kumar Mitra. He was one of the first in the world, to do this kind of manual assembly of this kind of a sounding device. And in those days, in the 1930s, actually, there were no, off-the-shelf items. Like nowadays, you go to a computer shop or to some other instrument shop and you simply buy some kind of a finished product. In those days, it was not there. So the scientists who were interested in doing any kind of study, not only radio waves, but any kind of study, they had to assemble their own instrument using the individual components. And so Professor Mitra, he did that, and he is highly regarded globally, not only in India. And his book, This Upper Atmosphere, is what we are still following, although it's more than, I think, 50 to 60 years old. But most of the material in that book is still relevant, particularly for textbook purpose. And also some of the research also which has been mentioned in that book, that is also still uh, prevalent. So this is the the field station that he had set up, and that is in North 24 Parganas, and so this is where his first manual ionospheric sounding system was put up. And at that time in 1949, when he started the radio physics department, when the department was first established, earlier there was a radio physics kind of a lab in the pure physics department. So he used to work from there. And then in 1949, our department was started, and we were the first to start postgraduate teaching in electronics at that time. And this field station was established in 1953. Although the place is known as Horinghata, but Horinghata is quite far from that, at least 10 to 15 kilometers away. It's right next to the Bidhan Chandra Krishi Vishwavidyalaya, about 50 kilometers northeast of Kolkata. And he assembled the first manual ionospheric sounding system, okay, in Asia in 1954, and he put it there. And the data from that used to be provided on a regular basis to some global data repository, okay. So that was very highly commendable in those days, okay. That means in the 1950s and 60s, on a regular basis sending the data, because in those days there were very little computer, no internet or nothing. So there were some kind of other techniques using which these data were transmitted on a regular basis to a global repository hosted in Colorado, USA. And that data is still available there. And this instrument actually, this instrument and its succeeding generations, they survive because single instrument cannot last from 1954 to say 1976 or 77. So it was gradually upgraded by other improved instruments. So that operated till about the end of 1977, 1978, around that time. And then one of the, this kind of a ionospheric sounding system, or ionosonde as the name goes, ionosonde, ionosonde. Whenever you find the name sonde or the term sonde at the end of a device name, you will immediately know that this is some kind of a active transmitting device. Whatever may be the nature of that signal which it is transmitting, it is an active device. That means it is transmitting on its own. It is not a passive device. A passive device means one which does not transmit on its own, but simply receives signal or receives some other input. So this kind of an ionosonde is still extremely important because it gives you a characterization. That means all the parameters that you need for establishing long distance communication, and it gives you information over a height range from starting about say 70 kilometer to nearly about 500 kilometer. Okay, so because the peak height of reflection or the peak height of ionization or electron density is typically around 350 to 400 kilometer. So the condition of reflection back of a signal transmitted from the surface of the earth upward. If you are transmitting a signal upward from the surface of the earth, following the physics that we had discussed earlier, that signal will be reflected back only till the peak of the ionization density, or till that height at which or up to which the ionization density is increasing as a function of frequency. Okay, so this is one such instrument, single instrument, although it's nearly, I think in 1926 this was first, this idea was first put forward by Brate and Tube, so it's nearly like 100 years back. But still, this single instrument and its new versions are considered universally as most versatile in designing any kind of long distance communication information. Now, on this note, let us just go back a little bit to one of the profiles that we had discussed earlier. That is, if we consider these profiles, okay, that means we could see that up to the height of maximum ionization, which is around 350 to 400 kilometer, usually it could be 300 also. It varies from day to day, from one place to another. So up to this height, whenever you transmit a signal upward, then it is passing from one medium to another and increasingly moving away from the normal, right? Because it is propagating from one medium having less value of radio refractive index to another medium which is having even lesser value of radio refractive index. So it is bending away from the normal. This is the terminology with which we are more familiar in optics. So eventually a state will come, a condition will come when it will be totally reflected back, and when it does have or when we does reach that condition, then of course if there is a finite separation between the transmitter and the receiver, the signal transmitted will be eventually received at the receiver. So that is fine. But one very simple question which you should try to answer is that we are transmitting a vertically incident signal, say for example, getting its reflection back, and from that reflected signal, following the condition of reflection that we derived, we are able to find out what is the critical frequency. And because the critical frequency is the highest frequency in the ground-based signal generator that we are transmitting and which is getting reflected back. So because critical frequency is related to electron or ionization density, you are able to tell that fine, this signal was reflected from this particular critical frequency. So the corresponding maximum value of that layer, electron density, will be this value, because you know that is 1.24 into 10 to the power 4 f squared from that relation. Fine. But how do we know about this top side? That means after this maximum has been reached and then above that the ionization or electron density, it falls rapidly with height. So how do we know about this layer? Because if you transmit a signal from the ground, that the maximum height up to which it will bend away from the normal and will be reflected back is the maximum height of ionization, not above that. So how do we know about the electron density or the ionization density at heights above the maximum height of ionization or electron density? Could any of you please try to answer this question? Just give me any suggestion. How do we do that? মানে সহজ করে বাংলায় বলছি যে তাহলে আমরা এই গ্রাউন্ড থেকে একটা সিগন্যাল ট্রান্সমিট করছি, সেটা it will bend away from the normal ততক্ষণ পর্যন্ত যতক্ষণ সেটা একটা ডেন্সার টু রেয়ারার মিডিয়ামে ট্রাভেল করছে এবং সেই কন্ডিশন অনুযায়ী সেটা আলটিমেটলি গিয়ে রিফ্লেক্টেড হবে এবং যখন ভার্টিক্যালি ট্রান্সমিট করছি দেন ইট উইল বি রিফ্লেক্টেড ব্যাক আপ টু দ্য হাইট অফ ম্যাক্সিমাম আয়নাইজেশন। কিন্তু তাহলে তার ওপরের এই যে লেয়ারগুলো মানে যখন সেটা ডিক্রিজ করছে হাইটের সাথে আয়নাইজেশন বা ইলেকট্রন ডেন্সিটি, how do we know or how do we calculate their values? That is my question. Any of you would please try to understand, please try to answer this question. How do we know about the top side ionization or electron density?
So satellite use kora hoy naki ami jani na.
Yes.
So do we use satellite or something like that for this?
দাঁড়াও আমি শুনতে পাচ্ছি না ঠিক করে। Yes.
Sir, আমি জানি না শিওর নই বাট আই এম আস্কিং দ্যাট কি স্যাটেলাইট এটা কি স্যাটেলাইট ইউজ করে করা যেতে পারে? Satellite based information.
Okay, if I accept your answer then just could you elaborate a little bit how? You don't have to tell me the instrument or something like that, the details of the instrument, but how could we do this?
Firstly, so sir, since the refractive index is decreasing, refraction করে তো আমাদের আর্থে ফিরে আসবে না ওইটা যখন ওই লেভেলে চলে যাচ্ছে টোটাল ইন্টারনাল রিফ্লেকশন।
Okay, Chirantan, okay, I accept some of your comments. The principle is just like that. That means because from a ground-based transmitter, when we are transmitting a signal, it is getting reflected back, or if it is transmitted at oblique incidence, then it will suffer some reflection, it will bend away from the normal and will be eventually received at a distant receiver. But if we try to put a transmitter on board a satellite, just like Chirantan suggested, and then when that satellite is passing through, suppose these heights or even higher, and it transmits a signal downwards. From the ground, we were transmitting upwards, but from the satellite, if it transmits the signal downwards, then looking down from the satellite, that radio wave will experience the same variability. That means the electron density is increasing as a function of height. তার ক্ষেত্রে height কিন্তু not this way increasing but the other way. Okay, because that transmitter is looking down, the signal is transmitted downwards, so it will follow the same principle. That means because the electron density is kind of increasing with height when you are looking down above this peak height, so it will once again follow this kind of a bending away from the normal, and then it will once again suffer total reflection and will be reflected back. So that kind of a instrument is what is known as a topside sounder. So if we just put the names of these instruments at least over here. So for this region we use the topside sounders, while for the lower heights up to the maximum height of ionization we will be using the ionosondes. So combining the outputs from these two, we could effectively regenerate the entire height profile of electron or ionization density at a particular time. And what is more important is that putting satellites is expensive, I understand that, but at least till the maximum height of ionization, you could achieve long distance communication information using ground based ionosondes only. Okay, and these ground based ionosondes, they would provide you with necessary critical frequency values, and from that critical frequency you will understand that what is the corresponding electron density through that relation, that 1.24 into 10 to the power 4. So as far as long distance radio communication is concerned, we do not need to have a topside sounder because that is a more expensive proposition, putting some transmitter on board a satellite, although it has been going on at least since 1980s onwards, or 1970s, late 1970s also. I think there were some satellites which were carrying this kind of transmitters for the topside profiling of ionization density. Now, moving on, let's go back. Because one of the fundamental differences between this branch of, science or technology with some of the others is that most of the observations in radio science were made first, and then we tried to explain those observations using the existing knowledge or theory or physics that we have. It is not the other way around. In most of the other branches of electronics or communication, you will find that you first come up with a theory, and from that theory you try to build some instrument or you try to validate that. But this radio sounding of the or this propagation of radio waves or different branches of radio science, they have not evolved in that fashion. There have been various observations which had been made earlier, and then those observations, we had tried to explain those observations using the known theory. So the principal parameters which are provided by these ionosondes, as they are known as, is of course the maximum height of this ionospheric F2 layer and the corresponding height of that layer, the critical frequencies, and then we will see that how actually it corresponds to, when we consider oblique incidence propagation situation. So what we had already discussed is that at vertical incidence, we know that as long as the frequency of the wave is less than the critical frequency, it will be reflected back by the ionosphere. And because the different layers, classically speaking, the different layers that we are till now familiar, like the D layer, the E layer, the F1 and the F2, they are not a single height. They are not at a single height. There is some thickness of those layers. Like the D layer, it extends from 60 to 90 kilometers. The E layer from 90 to say 110, something like that, or 130. The F1 from 130 to 210, and the F2 from 210 to about 400 or so. So these are not single heights. There is a thickness, there is a range of height corresponding to each of those layers. So how much depth will be penetrated by a particular radio signal, that will depend how close the frequency you are transmitting is to the critical frequency. Okay, that means suppose if the critical frequency of a particular layer is say 10 megahertz, just for example, then you will be receiving signals starting from say 7, 7.5, 7.9 or 8 and so on. That means corresponding to these reflections at the different frequencies, you are actually probing higher and higher into that particular layer. And eventually, when you reach 10 megahertz and you just increase it a little bit more, say 10.5, then from that layer you will stop getting a reflection. But remember, this is not like a digital system. Nature is not digital. Okay, that means it's not that you will receive from 10 and then at 10.1 there won't be anything. It's not like that. There is some kind of a gradual transition, but the instrument, the receiving instrument, is able to detect that difference. I mean, that information is provided, or that sensibility is provided to the receiving instrument in order to detect the difference between true reflected echo and some kind of a diffused echo, which happens when you have just crossed the critical frequency. So, theoretically speaking, above the critical frequency, the wave will penetrate the layer completely. And frequency which is greater than the critical, which would penetrate a particular ionized layer at vertical incidence, may be reflected back if it is incident obliquely. Okay, because you are making some kind of a transition from a vertical incidence propagation case condition to an oblique incidence. So, as we will see, there is some effect of the geometry as well. That means that angle at which you are making that particular signal incident on a layer, that has got some bearing on the fact that whether that particular layer, that particular signal will be reflected back or not. At vertical incidence, it might have penetrated that particular layer. But at oblique incidence, because some geometric angle is also involved, as we will see, so that particular frequency may be reflected back. Now, one of the other major achievement of late Professor Shishir Kumar Mitro was in the development of radars. Okay, it was he who around 1935 first put forward the idea that one could use radars for different kind of atmospheric remote sensing purpose as well. Okay, because before that, in 1935 means we are just at the threshold of Second World War. So around that Second World War time, the radars were extensively used only for military purpose and mostly by the Germans. Okay, so whether these radars they could be used for some other scientific studies other than military warfare, that was first put forward by him, Professor Shishir Kumar Mitro. And our department is actually building a radar at this field station around 50 megahertz, 53 megahertz exactly, the frequency at which this radar is being built now. So the principle of this ionospheric sounding, that means sending a signal up and getting its reflection back, that actually originated from the operation of radar during the Second World War primarily. It is still being continued. In those days, what was done was that whenever you detect some kind of an enemy warplane, you used to transmit a signal and get from the reflected echo, you understand that location and the velocity of that airplane. So that principle was used in later day radars also. in trying to get reflection back from different atmospheric layers or different atmospheric particles also. So our department is also building that kind of a radar, and hopefully in about 1 year time it will be completed. So maybe when situation improves and you will be able to move freely, then I think you will be still in the 3rd year or 4th year of your 4-year course. So we may consider a visit to that field station in order to get at least some kind of a first-hand knowledge of an active transmitting device. Okay. Okay, so I think I will stop here today and have your attendance now.